Welcome back, Chemistry 30. So this is the MS2.2 section, Intermolecular Forces. So we'll look at identify the intermolecular attractive forces, which include dispersion, dipole, hydrogen bonding, and ion dipole that exist between molecules or ions, and explain the concept of polarizability and how it relates to dispersion forces. Before we look at that, though, what we should talk about is the difference between intra and inter. So maybe just on the top of this page, we'll make a couple of notes here. So we'll look at intramolecular forces versus intermolecular forces. So let's make a little note of that. So first of all, what you can think of as inside the molecule or molecules versus outside the molecules. So the thing that holds the molecule together would be intra, and the force that holds another molecule next to another one, those are inter. So over here, we can look at what we've talked about. So we could have covalent bonding forces, and of course, we could break down into non-polar, polar, and then we could, so yeah, those are both covalent, weaker of the two. And then, of course, we have ionic. And of course, we could have metallic. I don't talk a lot about metallic type forces, but there are there as well. So we have that. So inside, so sharing, holding a molecule together, the atoms within that molecule are held together because they share electrons, versus one losing electron, one gaining electron, then being held by positive negative attraction. Or metallic, you have ions, positive ions, held together by electrons moving by them in an electron sea. That's kind of how that one works. And then moving, okay, so now outside a molecule, such as this. So inside, if we look at the picture down below here, so here you can see intramolecular, inside. So we could have electron sharing, such as over here, versus inter, which is in between, beside molecules. So with that one, we could have, as we'll see in this section, which is what this is all about, the force referred to as dispersion forces. Then we can have dipole type forces. Then we can have hydrogen bonding, as it's referred to. Then we can have ion dipole. And then, believe it or not, ionic bonding falls into this category as well, because it's kind of both, really. Two held together close by, but then what holds those two other ones, other positive negative ions? Well, it's still ionic bonding. So ionic bonding actually falls in both categories. And we can write down increasing strength, going from left to right. So those are a couple of notes we should put down there and pay attention to as we go through this little tour of intermolecular forces. Outside forces, outside the molecule that holds one molecule close to another one, right? So back to here. So the attraction between molecules, so that's inter, outside, are not nearly as strong as intra. So chances are of this molecule pulling this one apart is not that good, because this force holding it together, the inside force, is much stronger than the outside holding it close to another molecule. These intermolecular attractions are, however, strong enough to control physical properties such as boiling points, melting points, vapor pressures, and viscosities, how quick or how slow a liquid travels. The first two of these intermolecular forces are a group commonly referred to as van der Waals forces. So they're both a type of version of van der Waals named after the individual who studied them. The first one is dispersion forces, or sometimes referred to as London dispersion forces. Then we have dipole-dipole, hydrogen bonding, then ion and dipole forces. So in this video, we'll look at the dispersion forces first, and then in subsequent videos, we'll look at the rest of them. So London dispersion forces. While the electrons in the first orbital of a helium would repel each other and therefore tend to stay far away from each other, sometimes it happens that they wind up on the same side of an atom. So if we look at helium, we of course know there's 2 protons and 2 electrons. So common sense would tell us that, these electrons will stay as far apart from each other as possible because they're both like charges, they repel. Now, instead of envisioning this as a Bohr diagram, we envision it as an electron cloud, which is an area where the electron will be found. Okay, so an electron cloud is an area where the electron will be found. So they are run and constantly moving around, right? And as mentioned, what could happen is that they end up on the same side of the atom. So if we look over here, it could happen that on this atom, for example, the electrons are on the same side. So if they occur on the same side for a slight moment in time, using that, remember that delta symbol, which means partial charge. So this side could be partially negative, and of course the opposite side would automatically be partially positive. So if one side's negative, the other side's positive. So at that instant, then the helium atom would be polar. So it has charges on different sides of the atom. Charges on different sides of the atom. So over here it'd be on the left, that'd be negative, on the right it would be positive. And then what could happen is another helium atom could be sitting here, and its electrons just randomly moving. It would have a dipole induced. Now the word induced, you may have heard that it's caused to happen. Caused to happen. So you often hear about ladies giving birth, they're induced. So it's bringing about the birth, causing it to happen. So what happens here is that if this side's negative, well, all the electrons are going to be repelled, so they're going to move to that side, which is illustrated over here in this diagram. So we here's the train of thought here. So we go from here to here, then over here. Well, if this side's negative, it's going to cause the electrons on this side to be pushed over to here. Or I guess actually it could go from here to here, it doesn't matter. And of course this side would then be negative and this side would be positive. And notice what we're going to have here. We're going to have attraction, because slightly opposite charges are going to attract. So that's interesting how that works. So one molecule or atom becomes a temporary dipole, temporarily polar because of random electron movement, and then it causes other nearby atoms or molecules to become induced dipoles. So of course they attract. So London dispersion forces, put a star right here, or dispersion forces are attractions between an instantaneous dipole. Now that instantaneous dipole is just due to random movement, random electron movement. So due to random electron movement, and then it causes a nearby molecular atom to become a temporary dipole as well. Now these forces are present in everything. So everything has random electron movement. Makes sense because everything has electrons, so we will have random electron movement, which move to one side versus another, becoming a temporary dipole. Whether they are polar or nonpolar. So we can have polar molecules that do this or nonpolar ones. And then the tendency of an electron cloud to distort and have electrons combined to one side is called polarizability. Now, polarizability increases when valence electrons are further away. So we can think of it as it's almost like home. If kids are away from home, chances are they can do whatever they want and they aren't held by that attraction for home. Same thing here. The nucleus has a less of a hold on outer electrons in larger atoms. So it just goes to say that a larger atom will have more polarizability for two reasons. There's more electrons in a larger atom, and plus they're further away from the nucleus, so they can move around. So this is due to having more electrons, and and also further away, and also further away from the pole of the nucleus. Okay, so what I think I'll do is I'll stop there, and then we'll come back and talk about factors of dispersion forces, and then we'll maybe look at the assignment and the dispersion associated questions when we get back. All right, we'll see you again.